Hello. Hello and welcome to DAT330. My name is Andrei Zaychikov. I'm solution architect with AWS based out of Luxembourg. And today we're going to talk about how Sprinklr uses Amazon EBS to maximize its NoSQL deployment. I would like to ask you to welcome Sprinklr team, Jamal Matskar, who is the head of infrastructure and DevOps in Sprinklr, and Gopala Krishna, who is a platform architect in Sprinklr. Today we're going to talk about how and why to choose NoSQL database for your solutions. And of course, we're going to talk about some introduction and internal stuff, how MongoDB works. And we're going to cover some various aspects of designing your geo-distributed clusters for global deployments. And for sure, we're going to go through Sprinklr implementation and challenges, including database they use and the scale of these databases, topology for MongoDB deployment, some operational challenges they faced with, and of course, how they address these challenges. I would like to start with answering one question. What is the reason for NoSQL rise? Because it's kind of important to understand why we are using these types of databases. First thing which is important is complexity of data schemas. Because during the life cycle of the project, data schemas in relational databases can become more and more complex and can bring a lot of issues from terms of operational terms, right, from different performance issues and so on. The second thing is the data volume. And as during the last years and during even these minutes, the data volumes we are processing they're growing significantly. And normal way of handling a vertical scaling doesn't work anymore, especially for geo-distributed deployments. And that's something where NoSQL shines, really. And the next thing, last but not least, is uptime and latency. So for NoSQL databases, normally you can have much higher uptime, and you can satisfy a kind of high SLA, especially which is important for B2C projects and so on. And with geo-distributed features, you can distribute your databases across the world, and you can bring your database as close to your customers as it's possible, depending on the infrastructure you use, of course. NoSQL ecosystem nowadays, it's quite the big one. There are actually hundreds of different databases out there in the wild, right? Some of them are really well-known, like MongoDB, Cassandra, RSpike, but there are some others which are not as well-known. So it's kind of a problem of how to pick up the proper database for your deployment. Of course, we have on AWS, we have our own understanding of NoSQL, and we have different options for deployment of NoSQL solutions like Amazon DynamoDB, which is super fast, and key value storage. It's really nice and plays well with most of deployments. Of course, you can do Amazon data lake on Amazon S3 and use Athena to query your data, so it can be quite an approach like a database and data lake kind of approach. And you can have your clusters based on EC2 and EBS, so it's kind of DIY solutions. Before you start picking up the right database for your solutions, you have to answer one simple question. Do you really need distributed NoSQL clusters for your deployments? For most cases, still nowadays, relational databases are like a Swiss Army knife for most of the use cases. But if you have really unclear load, if you have bursty workloads, if you need really high uptime, if your users are globally distributed, or you have a huge data volume, then probably you will need NoSQL database. There are three kind of approaches to picking up the proper NoSQL database for your deployment. One is kind of almost no real choice, right? If you have legislation constraints, if you have your homegrown expertise and you don't want to spend some time accommodating new technologies, or for example, if you have some hybrid or legacy solutions, you don't need to really make a choice, right? The next thing is a will to experiment. It's kind of a really good thing. We're all experimenting all the time. So there are plenty of databases, you saw that, and you can pick one which better suits your use case and the things you're trying to achieve. But you have to admit and you have to mitigate the specific challenges for not very mature technologies. And the last but not least, it's like one of the most important things, it's informant choice. So for example, if you really need something which is highly available, which has a high throughput, but you don't want to have a lot of issues with operations and so on, you can go for DynamoDB. Same for reliability from the hardware perspective, from networking and so on. If you need some pure performance, like let's say data streaming platform or caching or in-memory key value data stores, you can use Redis, Memcache, Kafka, or Spike. There are plenty of them on the market. If we're going to talk about like really big clusters, geo-distributed clusters handling a high throughput and a lot of load on that, we're going to talk about MongoDB, Cassandra, React, Couchbase, and some other databases like that. And of course, you can pick up the database based on your requirements for data schema. Like let's say for graph databases, you can go for Neo4j, for Janus, or something else, or like Solr and Elasticsearch for arbitrary queries and so on. So today we're going to talk mostly about MongoDB. So it's kind of a crash course of how MongoDB works. On the right-hand side, you can see how MongoDB is organized on the cluster level. On the left-hand side, how it's organized on the node level. So on the cluster level, MongoDB uses sharded clusters, which consist of shards, and shard effectively is a replica set. And within the replica set, you can have master nodes and one or more secondary nodes, or even no secondary nodes, right? In addition, you can have special types of nodes, arbiter nodes, node for election procedure, and shadow node like to make backups and so on. In configuration, in the cluster itself, in sharded cluster, you can have and you must have a configuration replica set which holds the information about where the data resides, how it's organized between the shards, between the nodes, and so on. On the node level, we can see it's a read and write process for data. Dotted line is the write process, and the solid line is the read process. So MongoDB reads and writes through memory, and it writes firstly to the journal, and after journal becomes a certain size, or it's sometime after a certain amount of time, like let's say 100 milliseconds, it's flushed on disk and then becomes BSON. It's a binary format which is actually stored on disk. In BSON, documents are stored in extents. Actually, this is specific data structure which holds some metadata in BSON itself, and of course, it has some indexes built on that to show where actually the data is on disk. As you can imagine, BSON is a binary document, right? So which means that when the data is deleted or like something goes wrong, like something is updated, or you inserted a new nested documents, the fragmentation can occur. And the thing is, like as MongoDB reads and writes through memory, the fragmentation can occur both in memory and on disk. So Jamal, can you please tell us a bit more about your use case and what was your approach in Sprinklr to pick up the right database for your NoSQL deployment?
Thank you, Andre. Before I talk about, we talk about the Sprinklr use of databases, let me give a little bit overview of Sprinklr so you have some more context of what we do. Sprinklr is the first unified customer experience management platform for the enterprise. We help world's largest brands, including Amazon, to do marketing, advertising, commerce, care, research, on Facebook, Twitter, LinkedIn, and 22 other social channels globally, all on one integrated platform. Our customers can integrate Sprinklr with their legacy systems like CRM to get a unified system of engagement for their employees to work together across silos in real time to manage customer experience at scale. This is a very high-level view of our architecture. The most interesting aspect for our architecture is on the top right, where you see a list of all the social channels that we are integrated with. We are integrated with all social media channels. We get data from these channels, we analyze them, we process it, we do sentiment analysis, and we may provide meaningful insights to the user of our platform. The users of our platform can use our application to engage and listen to their customers on any social channel. Since we are integrated with all these social media channels, we get a lot of data every day. We process billions of transactions. We have petabytes of data, thousands of servers across different geolocations. Just to put things in perspective, from Twitter alone, daily we get few 100 million tweets every day. This is a very high-level network overview how we have done the deployment. So if you can see, we have different layers of security. We run everything within VPC. Our front-end servers are running in the web security group. Then we have a middle layer security group for our middleware data services. And then the last and the most important one is all our data store. So the data store as security group is the one which has the most restrictive ingress and egress rules. And this is where we make sure that it's difficult to penetrate. All our services on the front end in web tier, we put load balancers. And the reason we do that is because AWS load balancer provides an extra layer of security against any potential DDoS attack. This is a list of some of the technologies that we use. We use several AWS services. We use several open source products. And then we also use Ansible and Jenkins for our build and automation. Mostly we are running Java on Linux. In terms of automation, we have also written a lot of custom code. We have written probably more than 1 million lines of code to just manage infrastructure at a scale. So now I'll hand it over to Krishna to talk about our database journey.
Thanks, Jamal. Initially, we were storing all types of data in MySQL. Once data increased more than 100 million records, we started seeing the slowness in aggregation queries. So we started writing the data in Solr as well and redirecting all our aggregation queries to the Solr. This worked for us for a couple of years. Once data increased more than 200 million records, we started seeing the slowness in MySQL write operations. So we decided to migrate all our big tables data from MySQL to sharded Mongo clusters. Once we migrated all the big tables data to Mongo sharded cluster, and we were writing data in Solr as well, and all our aggregation queries are redirected to Solr. This has worked great for a couple more years. Once data increased more than 800 million records, we started seeing the issues in Solr. We started seeing the issues related to load and GC issues in Solr. We want to horizontally scale this Solr deployment, so we tried with the Solr Cloud. In Solr Cloud, we faced issues related to the data balancing and incremental backups. So we slowly moving from Solr to Elasticsearch. Elasticsearch is scaling great for us with the billions of records. How big is our database deployment? We have more than 1,300 servers in Elasticsearch. And the second largest deployment is MongoDB, which has 900 plus servers. And Solr is being replaced with the Elasticsearch. We have right now 380 servers. Still, we use RDS servers for transactional related operations. We have 70 multi-AZ RDS servers. Handing over to the Andre to talk about choosing the right geo.
So if you can imagine, it's a massive deployment, right? More than 900 of servers for MongoDB, it's quite big. And I often see the situation when the customers start their deployment, like a small startup, we're going to choose some random geography, like for sake of the cost, for example, or for latency for our developers. And after a certain amount of time, when like the user base grows and the number of requests grows, the data set grows, often such customers experience really bad problems with latency, because one customer had, for example, their deployment in Europe, but most of their customers were located in US, and they had to provide like a really big project for migration of data of their NoSQL databases from Europe to US, which wasn't funny, actually. So you have to think carefully about where your data is, where are your users, and how you will deploy it. And of course, with MongoDB, for example, with the sharded clusters, what you can do hybrid deployments for some like data locality laws and stuff like that. Okay, after choosing your geo, you have to design the deployment architecture for your NoSQL databases, right? First thing is the network, of course. You have to take care about that, and you have to be sure that the network works and the different parts of the cluster can work together. After that, you have to design and pick up the proper types of the instances of the storage, and you have to design how many nodes, general nodes will be there, like master and secondaries, and you have to design how many special nodes will be there in your deployment, like hiddens and arbiter nodes, and where they will be located. And we're going to cover that in more details later on. And of course, you have to think about service discovery, like where's the configuration replica set for MongoDB sets. You have to think about access patterns and read and write consistency. So what will be your setup, what will be your configuration for read and write, and you have to replay that for different edge cases for your database. So for example, what you can do here is like to deploy a MongoDB sharded cluster in 3 different locations. It's a kind of hybrid example, right? The only thing to think about, and the big trade-off, is the deployment of ReplicaSet, of the configuration ReplicaSet. So one approach is you can deploy it in one region close to the biggest, let's say, deployment of MongoDB, or you can distribute that across the regions in this case, right? The trade-off of distribution is that the shuffling of data will be slow, and you can experience some bad situations with latency for writes. So you have to think about it, and that's where access patterns really matter. After that, you have to design the application interactions with your database. The first thing, which is really super important, is error handling inside the application, because it gives you a lot of interesting information around how actually your application works, how your cluster works, how they accommodate load, and so on and so forth. So error handling is super important. The next thing is DB requests. So normally, we're saying that MongoDB is schemaless database. That's true. However, there are some certain recommendations around how the document should look like, not to use a lot of nested documents, not to scan inside the documents, and so on. So there are certain recommendations. And you can, of course, you can plan and design your indexes. MongoDB interacts with the application with the use of MongoAS process, so you have to fine-tune this process depending on the use case as well. And of course, don't forget about network connectivity on the database cluster side, and it links with consistency levels and consistency guarantees. If the network is there, it's not working, nodes cannot communicate with each other, most probably you will not be able to read or write data on the levels of, and with the guarantees you want. So if we're going to talk about like really real geo-distributed deployments, what we can use, you can benefit from L4 load balancing on top of MongoAS processes, which will help you to implement some interesting logic around like routing and request throttling in case one of the big deployments just fails completely. So, and we're going to cover that in more details. And of course, you have to plan the configuration replica set and request throttling, driver errors, and look for slow queries and some schema issues. So, Krishna, can you give us some rough numbers around how your MongoDB works?
Yeah. Let's look at some numbers to understand at what scale we are operating MongoDB. We have 900 plus servers. And each servers, we attach one EBS disk, which is ranging from 500 GB to 4 terabytes. And we have 200 terabytes of compressed primary data. And we keep 2 secondary nodes in each replica set. That means we have 600 terabytes of compressed data across our MongoDB deployment. In terms of replica sets, we have 250 replica sets and 20 sharded clusters. And some of the sharded clusters holding 30 shards, and which can hold up to 30 terabytes of data. And coming to number of operations we do on our MongoDB deployment is 2 million Mongo operations per second. We have daily 30 terabytes of data changes are there, and these 30 terabytes of data we sync from east region to west region for disaster recovery purpose.
So for such deployments, and it's quite big, right? 2 million of operations and like terabytes and terabytes of data. You don't want to lose these data, the whole data set, right? And you don't want your users to experience some issues with connectivity, some issues that with throttlet requests and so on. So you have to plan a high availability and disaster recovery. So from high availability standpoint, there are certain aspects, right? So the most important part is on your application side, let's say. So your application should know that if this part of the cluster fails, it can go to another part of the cluster, right? And to process the request there. You have to have authentication configurations, routing and load balancing from your application side. And one really important thing is that you need to be able to throttle these requests, because as you can see on this diagram, if let's say one of the regions just fails completely and you're not able to request to process requests there, the whole amount of traffic, for example, can be routed to another region. And if it's like 42% more load, which comes out of nowhere, it can be really challenging, right? So you have to be prepared to scale out these parts of the clusters. For MongoDB, there is a classic setup with master and 2 secondary nodes and with hidden nodes for the deployments. But if we're going to talk about 2 AZs in one region and 2 AZ deployment for the classic setup, it can have some edge cases. So for example, if one AZ fails and your master and secondary node was in that AZ, so you will be only able to have a level of concerns of local reads, sorry. So you only will be able to read some data from this secondary node. So there are some techniques. So you can, for example, use the predictable elections. So set up the weights for elections. You can use master hidden node if setup if your application can tolerate with some downtime, or you can use a remote node in ReplicaSet. Krishna, and what's your approach for DR? How you do that?
Yeah, in a sharded cluster, each shard is a replica set. Let's look at replica set topology. In a replica set, all writes happens through the primary data node, and all these writes tracked inside Mongo collection called oplog. And we add one more data node to the replica set for the high availability purpose. From primary to secondary, replication happens through the oplog collection. When primary data node goes down, secondary data node should re-elected as a primary. For this reason, for re-election to happen, at least more than half of the voting members should be available in a replica set. So we add one arbiter to the replica set in third zone. We add one more data node to the replica set as a hidden secondary. From this, we take daily backups. Okay, let's see what are the challenges we faced with our MongoDB deployment. The first challenge we faced with the backups. Why? Because while we migrating from MySQL to Mongo, our primary concern was scaling up the writes. So we launched all our data nodes with the instance store volumes, hi1.4x servers, which has 2 terabytes of instance store volume. So our data is there on instance store, we cannot take the snapshots. So we had a couple of options for this backups. The first option was Mongo dumps. But Mongo dump does not support incremental backups. And in our case, we used to see this Mongo dump process speed is around, it used to take 1 hour for dumping the 50 GB of data. with large deployments like Sprinklr, this is not a feasible solution. Then we tried with the second option, that is file system copy using rsync. With the rsync method, we are able to do the delta sync, but this process used to take more than 2 hours. While backup process is going on, we have to stop the writes on hidden secondary. And if you want to take multiple backups, we have to do the rsync from the start on new volume. This used to take more than 15 hours. So with all these pain points, we decided to migrate all our HS hidden secondary data to the EBS volumes. Once we migrated all our data to the EBS volumes, we are able to take multiple backups using EBS snapshots. And our backup process time has reduced from couple of hours to 10 minutes, less than 10 minutes. And the amount of time you have to lock the hidden secondary was reduced to less than 1 minute. And as these EBS snapshots are incremental, and even though we maintain multiple EBS snapshots, the backup cost has reduced significantly. The next challenge we faced with the data node recovery, as still our primary and secondary data on instance stores, if any of the data node goes down, we have to rebuild the data node. As data size is huge on our replica sets, it used to take lots of time. We had a couple of options for building the data node. The first option was, as we have already EBS snapshots, so copying all the data from EBS snapshots to instance store. This used to take more than 15 hours in our case. The second option what we had is Mongo sync. Just add back the server to the replica set, and Mongo syncs all this data to the new node. This happens in 3 steps. In the first step, the new node copies all data from the primary data node. Once all the data is copied to the local, it builds the indexes based on the metadata. Once index creation is completed, it syncs all the write operations from the step onto current time. In our case, this whole process used to take more than 2 to 4 days because of data size and because of the number of indexes we have and the complexity of our indexes. So as it used to take 4 days, at least we have to maintain 4 days of operations in our oplog across all our data nodes. And as this is a full sync, it used to put extra load on primary servers. And all these 4 days, we have a great risk at high availability. So with all these problems, we decided to migrate instance store volumes data to EBS. We migrated all our primary and secondary data to the EBS in 2 steps. In the first step, we migrated all data to IO1 volumes. How did we do this without impacting application? We added 2 hidden secondaries from the EBS snapshots to each replica set. We waited a couple of days to make sure the read and write latencies has come down to less than 1 millisecond. Then we promoted one of the hidden secondary as a primary, and we monitored read and write latencies for a couple of weeks. Once we are happy with the read and write latencies, we removed all instance store servers. In the second step, we migrated all our data from IO1 to GP2. We followed the same procedure. With this migration, we are able to recover our data nodes much quickly. Previously, it used to take 4 days. That process has come down to 1 or 2 hours. And also, with this process, we are able to separate computing power and storage. This helped us scaling up or scaling down computing power when we required. And with the EBS, the volume size increases. It becomes so easy. It's just a couple of clicks. As our data node recovery time has reduced to a couple of hours, we reduced our oplog size to hold at least of 24 hours of operations. The next challenge we faced with the disaster recovery process implementation. In disaster recovery implementation process, mainly we have 3 major tasks. One is regularly taking backups. The most of our backup issues are resolved by using EBS snapshots. The second one is copying all this data to the DR side. As we have around 30 terabytes of data changes daily, initially it used to take more than 24 hours to sync this data from east side to west side. We worked with the AWS team to increase our bandwidth limits and to increase number of snapshots we can copy from east side to west side. After increasing these limits, we are able to transfer all 30 terabytes of data in less than 4 hours. The next challenge we faced in restoration process. In the restoration, the first thing is launching thousands of servers and creating volumes from the snapshots and attaching those volumes to the servers. Once attachment is done, we have to start the Mongo process. While starting the Mongo process, we were seeing Mongo startup was taking more than an hour. So we worked with the DB team, MongoDB team, to understand why startup is taking more than an hour. Just startup is taking more than an hour. So finally, we come to know that it's all related to oplog and oplog milestones. What are these oplog milestones? Mongo internally maintains milestones against the oplog collection to efficiently remove the oldest oplog entries from the collection when it reaches the maximum size. And these oplog milestones are not persistent. That means whenever Mongo restart happens, it will choose the new milestones. Because we have oplog size more than 100 GB in most of our replica sets, and this data has restored from the EBS snapshots, the milestones choosing was taking the most of the time. So we worked with the MongoDB development team and implemented optimization in backup and restoration process. In the backup process, we added a couple more steps. Before taking the snapshot, we restart Mongo as a standalone mode and take the latest oplog entry to the temporary collection and trigger a snapshot. And once this snapshot is available in DR side, after restoring it, just remove the oplog files and recreate the oplog file with the just headers and start Mongo process in standalone mode and copy back the oplog entry from temporary collection to oplog collection. Once we restart Mongo process in a ReplicaSet mode, in this case, it has to scan only one record for choosing the new milestones. This reduced Mongo startup time. With this process, after implementing this process, Mongo startup time was taking around 30 seconds. Before that, it was taking around 80 plus minutes. Okay. Next comes to workload. We do over 2 million operations per second on our MongoDB deployment. How did we get this 2 million number? If you check this, in one of our primary data node, we do around 2,000 insert operations and 6 to 7K of read operations, and deletes, updates, and get more. All this will be around 1,000 operations. On each and every primary data node, we do on an average more than 10,000 operations per second. Comes to write workload. Some of our modules produce heavy data, and all this data we will store it in Mongo. So we have seen some of our Mongo replica sets were able to handle 80 GB of data per hour. Okay. With this heavy write and read workloads, what and all performance metrics we are getting it from the EBS. Once we restored from the snapshot, the first couple of hours, the average write latency is around 50 milliseconds. This is very huge. But once most of the blocks are local, the average write latency has come down to less than 5 milliseconds. The same case with the read latencies as well. Initially, first couple of hours, the read latencies were around 70 to 80 milliseconds on an average. Once most of the data blocks are there on the local, the read latencies has come down to less than 10 milliseconds. In most of our replica sets, the read latencies are around sub-milliseconds. Okay. Next comes to cost savings. The first cost savings, we got it from the replacing expensive HI 1.4x class servers with the R3 servers. Now we are replacing with the R4 series servers. The next cost savings, we got it from the backups. As EBS snapshots are incremental, we are able to save lots of money in backups. The next one is white tiger compression. Mongo introduced white tiger compression from 3.0 version onwards. Because of this white tiger compression, we were able to reduce our data size on the disk about 60%. And we changed all our data from IO1 disks to GP2 disks, and dynamic volume changes. From EBS, without detaching the volume from the server, we are able to increase volume size. This helped us while launching the new replica sets, launch with the minimum size of disk, and as data grows, increase the volume size. And with all these cost initiatives, we are able to save our Mongo storage cost from $155K to just $53K per month. This is almost 66% of savings. This is a huge win for us. Handing over to Jamal to talk about security.
Thank you, Krishna. So this is a different view of the security that I talked about earlier. It just gives a little bit more details. We use various AWS services. We run everything in VPC, and there are different security groups for a different layer of architecture. The two important things I want to highlight here is, one is that we use server roles, IAM roles for all our internal services or API calls. And we do this because we don't want to deal with the API keys sitting around here and there. So that makes the life very easy. Second thing that we do is we use EBS encryption. And this is something which works very well. Initially, when we were trying the encryption, we were not sure how it will perform. But after we enabled it, we didn't see any noticeable performance issues with using the EBS encryption. So, and we don't have to worry about any key management either. This is another thing which is a very interesting feature which I like, which works like magic. Because we are running our primary infrastructure in Virginia, and we have the disaster recovery in Oregon. So if you are using encryption, you need to have the keys available in both regions. In our case, some of our customers are very security sensitive. They don't want the key to leave the primary region. They want the key to stay on the physical hardware in the primary region. So in this kind of scenario, if you have to manage encryption across 2 different regions, then you have to decrypt the data in Virginia, send it over securely to Oregon, then re-encrypt it again in Oregon again using the key in Oregon. So this is and you have to manage the key in both regions. So this whole thing, operation, we don't have to do anything using EBS. It happens behind the scene for us like a magic. So I will hand it over to Andre now to talk about how to pick the optimal storage and instance type.
Thanks, Jamal. And you guys have a great deployment and a huge system, right? But we completely understand that like every use case, it's different, it's unique. So that's why there are a couple of hints around how to pick up the proper instance and storage types for your deployments. Of course, everything depends on database implementation, on your data schema, on access patterns, and it's something always to consider. But what you can do is to use these benchmarks. The benchmark has 2 axes. So one is requests per second, another one is the volume size, right? So for MongoDB and general workloads without much pressure on the database and with different sizes of the data set, you can use mForce with GP2 volumes. It's kind of a standard and pretty good working on most of the use cases. But if you have something like, if you need really high throughput, if you need a lot of read and write operations per node, for your MongoDB deployment, and your data set is relatively small, you can go with instant stores and you can use iFreeze or i2s. But while your data set grows and you have more and more data on the nodes, as the guys showed us, it's worth using rForce with GP2 volumes because they are cost effective. They have a lot of nice features like encryption, elastic volumes. You can just increase the amount of I/O per volume and increase the size of volume on the fly. Snapshotting and encryption for snapshots and a lot of interesting features. And for hidden nodes, you can use mForce with GP2s, even though if your deployment is on top of iFreeze, it's better to use mForce with GP2s for hidden nodes because you will be able to do a backups quite fast and efficient way. We are not covering Cassandra in these talks, but just to show you, to give you an idea how database implementation affects the process for picking up the right instances storage type, I put Cassandra here as well. So for Cassandra, the general recommendations are the same, but if you have really high throughput on writes, what you would do, you will use cForce most probably with GP2 volumes and ST1 volumes for commit log. Why? Because Cassandra is bounded, CPU bounded on writes, so you're going to use most probably cForce. So for different databases, different use cases, different access patterns, there can be different types of volumes and different types of fine-tuning on your database side. So we consider, in our practice, what we can see is that picking up the proper instance and storage type is kind of a journey. It's not like set up in stone, and it's not going to change anytime, right? So we all start small, and normally all the products, all the startups start with a small amount of data, small clusters, and there you can use mForce until your customer base grows significantly, and you will need, for example, i2s or iFreeze with instant stores to accommodate that load. But as your data volume grows and up to the certain moment, you can reconsider and you can go back, for example, to EBS volume because it will help you with operations and it will be much more cost effective. So, Krishna, can you please sum up our today's talk?
We are able to run our large-scale Mongo deployment on EBS, and it helped us solving some of the critical operational challenges. The first one is backups. We are able to take multiple snapshots, multiple backups using EBS snapshots. The second one is high availability SLA has improved. We are able to reduce our data node recovery time from days to less than an hour. And also our read and write latencies has come down to sub-millisecond. The next one is cost savings. We are able to save around 66% of cost on our Mongo storage. The last one, with the help of cross-region snapshot transfer, we are able to implement our DR process with the acceptable RTO and RPOs. Thank you.
Thank you. And I think it's time for your questions. If you have any questions, there are microphones set up, so you can use one. Thank you.
Hi, tell me please, have you implemented some technique for warming up volumes after restoring from snapshots? You will have cold data and much more latency after restoring.
Yes, we can run some simple shell script to warm up the data, but in our case, we did not do. We let it Mongo to warm up the data on its own.
Mm-hmm. Thank you. And second question, where is your Mongoose is placed? It is dedicated EC2 instances with balancer, or maybe it is right near application?
No, it's on dedicated balancers. All MongoS are dedicated on dedicated balancer servers. It's not on application servers.
Okay, thank you.
Thank you.
Hello. So you're using Mongo no relational. You're hosting it on AWS. Have you thought about just moving to DynamoDB?
I think I can answer that. One of the things is that we do run on multiple clouds. So a little bit in our case, we have to do be cloud agnostic. So some of the infrastructure that we have built and optimized, and historically, I mean, it's a huge deployment. So A, logistically, it's not easy. B, we also want to keep it a little bit less tightly coupled to the cloud infrastructure that we are running on. So those are the two main reasons. Otherwise, yeah, I mean, we have looked into that. And a lot of the times at our scale, what happens is that cost efficiency wise is another thing to think about, because in some services we have noticed that the scale that we are running it, because we get all the discounts and volumes and other things, using a dedicated service, there is always a little bit markup, and that for us makes a big difference on cost.
So I might have just missed something, but how do you account for the performance difference between IOPS and GP2? Have you seen any IO drop off moving from an IOPS EBS storage to a lower tier? Or am I just missing that?
No, I think it depends on the size of the volume that you're using, and also how much operations you're doing. So EBS volumes can handle anywhere like 3,000, 10,000, they can burst up. So as long as your IO operations are within that range, EBS volumes were great. We do use for Elasticsearch SSD, but in that case, some of our IO operations you're talking about 80,000 IOPS. So that's a different use case. But I think for our Mongo use case specifically, we didn't see that issue with using EBS volumes.
Okay.
And in fact, we started out with provision IOPS, and then when we noticed the load, we realized that we can actually do fine with GP2 volumes.
Do you know what load level you GP2 doesn't work for you anymore, and you needed to do a higher like.
I think there is like specs that you can look at for the EBS. I don't know the exact number right now, but it can burst up. Maybe I don't know, Andre, if you know in our case, like the Elasticsearch, 80,000. Maybe I think like 10 to 20,000. When you start going beyond that, you may want to look into SSDs.
So, okay, thank you all, and have a nice day. If you have some other follow-up questions, we're staying here for some time. So thank you guys for attending.